Good afternoon, dear colleagues. I'm glad to see you all here this day. Today I would like to tell you about the plasmodynamic synthesis of titanium dioxide. The photocatalysis of water using semiconductor materials is one of the most promising methods of water and air purification. Despite the fact that in recent years a huge number of materials which can be potentially suitable for various photocatalytic applications have been investigated, titanium dioxide still remains the most widespread photocatalyst due to its high photoactivity, chemical alertness, low toxicity, environmental friendliness, and low cost. Among the all known titanium dioxide modifications, anatase is a preferred polymorph in photocatalysis due to its higher photoactivity in comparison with rutile structure. Unfortunately, there are two main restrictions on the applications of titanium dioxide as a photocatalysis. First of all, there is the band gap, which that corresponds to the light absorption only in the ultraviolet spectrum region. In addition, titanium dioxide is characterized by the rapid recombination of photogenerated electron-hole pairs and a correspondingly high overvoltage for water splitting, which leads to a photocatalytic reaction efficiency. Thus, obtaining titanium dioxide-based material with a wide spectral absorption range in the visible light region and with a high photocatalytic activity is an urgent problem. Among the methods for synthesizing materials, it's worth highlighting the plasmodynamic synthesis method. The plasmodynamic synthesis method stands out against the background of other methods for its versatility, environmental friendliness, and the use of cheap and non-toxic precursors. Short synthesis time, the possibility of obtaining ultra and non-dispersed particles of different morphological types, the broad control of the phase and particle size distribution by varying the experimental parameters, prevented detected, doped, and metastable structures. The plasmodynamic synthesis method was carried out using the plasmodynamic synthesis system based on a high current pulse coaxial magnetoplasma accelerator of erosion type with titanium electrodes. In the process of the operation, the accelerator generates a plasma structure in the electrode barrel. As the jet moves, here, erosion of the electrode barrel occurs, eroded materials enter the plasma, thereby producing the main material, titanium. The outflow of the plasma jet occurs in the central volume of reactor chamber filled with a gaseous mixture of argon and oxygen, where is the plasma chemical synthesis of nanoparticles. Now we will look at some investigations. First of all, the product of plasmodynamic synthesis is analyzed by scanning electron microscopy. Assessing the brightness and contrast of the image, we can conclude that the obtained material consists of the product consists of materials that are close in density. Moreover, almost all particles have spherical shapes. The particle size distribution histogram shows that the largest number of particle size have a size of 80 nanometers. The main factor influencing the phase composition of the product is the oxygen concentration. Therefore, a series of experiments was carried out that changed this parameter from 5 to 8%. This slide shows diffraction patterns of powdered material synthesized at various values of oxygen concentration. Two crystalline modifications of titanium dioxide were revealed, anatase and rutile. As can be seen, a variation of oxygen concentration leads to a significant increase in the percentage of the anatase crystalline phase in the synthesis product composition, which is characterized in an increase in the intensity of the main reflection of the anatase. Quantitative analysis of the anatase content made it possible to establish that When the oxygen concentration in the reactor chamber exceeds 30%, the phase composition of the resulting product is stabilized. In addition, an increase in the oxygen concentration makes it possible to control the average size of coherent scattering regions for the synthesized anatase phase. Since the plasma dynamic synthesis process has a pulse nature with the formation of characteristic shock wave structure of a plasma flow in the reactor chamber, it is logical to assume that the second key factor affecting the phase composition of the synthesized product is the process energy. Thus, a series of experimental studies was carried out with the change in the range of the supplied energy, approximately from 20 to 40 kilojoules, to assess this effect on the phase composition and structure of synthesized particles. The diffraction patterns products synthesized at minimum and maximum possible value of the supplied energy show that the higher value of the supplied energy has a positive effect on an increase in the anatase in the final product composition. This fact is confirmed by the curve on the change on the anatase content depending on the supplied energy value. At the same time, there is a certain energy limit above which there is no change in the product composition. According to the calculations, the average level of coherent scattering regions values for the anatase structure is 70 nanometers. The morphology, crystal structure, and particle structure of the powders were analyzed using a transmission electron microscopy, including high-resolution TEM. A preliminary analysis of the TEM data for powders synthesized at various oxygen concentration and supply energies showed the absence of qualitative differences in the morphological composition particles. Therefore, the slides show a typical bright field TEM image and corresponding micrograph of the powder obtained at specified parameters. The given microdiffraction is characterized by the presence of point reflections attributed to only two modifications of titanium dioxide, anatase and rutile. The detailed studies of bright field and dark field images in the light of different reflections allowed us to assign the particles less than 200 nanometers in size and characterized by geometrically correct capacity to the anatase structure. As can be seen in the TEM images in the slide. It was found that these nanoparticles have a monocrystalline structure. However, the shapeless objects of various configurations having sizes of several hundred nanometers were attributed to rutile phase because the luminous closed diffraction contrast in the body of such particles are only seen in the light of diffracted beams of the planes of the rutile structure. More detailed studies of crystal structure for synthesized particles were made using high-resolution transmission electron microscopy. The measurement of the interplanar distances for main reflections indicated their closeness to the reference values of the anatase phase. The formation of planar package with the interplanar distance 351 nanometers, which correspond to crystal plane in the direction 101 of anatase phase. The structure, which is typical for the tetragonal system with a rectangle in the base with sides A and C, is clearly visible that are close for the theoretical values for the elementary lattice. However, such an order structure is not found in all anatase particles. In the slide images with a set of crystal planes of various directions of anatase and rutile are presented to show highly disruptive or disordered crystal structure. In most cases, the formation of defect structure is observed. The appearance of such dislocations is usually caused by mechanical shear stresses, which in this case are the result of shock waves arising in the plasma dynamic synthesis process. The defectiveness of the characteristics obtained product also was investigated by the XPS method, the results of which are shown in the slide. According to the obtained spectrum, it is obvious that the main maxima in the product are oxygen 1C and titanium 2P. The titanium 2P maximum, the convolution shows two peaks with the specified binding energies. These data show that only titanium with the valence 4+ is presented in the synthesized product, which is characteristic of stoichiometric titanium dioxide. After deconvoluting the oxygen 1C maximum, the presence of two peaks with specified binding energies was revealed. The primary peak at the binding energy of 530.1 electron volts correspond to the bulk or lattice oxygen and titanium dioxide, while the secondary peak is assigned to defect oxygen size corresponding to an oxygen atom germinal to the lattice oxygen vacancy. Thus, XPS studies also confirmed the formation of defective titanium dioxide structures in the plasma dynamic synthesis process. It is known that the materials, it is known that the material defectiveness can affect the optical characteristics, which are directly related to its catalytic applications. In this regard, the optical characteristics of obtained products were studied by diffuse reflection spectroscopy. The resulting curves of the dependency of the diffuse reflection coefficient on the wavelengths were obtained. The band gap determination was carried out to the edge of the main optical absorption band. For this, the obtained reflection spectra were transformed using the classical Kabel-Mann function. Curves for the synthesized powder in comparison with the standard powder titanium dioxide GDP2021 are shown in the slide. The optical absorption edge in the case of plasma dynamic synthesis product is shifted from the ultraviolet to the visible region. The difference in the band gap band value is directly related to the crystal structure defectiveness of the plasma dynamic synthesis product, which appears due to the dynamic conditions in the shock wave structure medium. The results of the synthesis of ultrafine titanium dioxide in a hypersonic jet of the electric discharge plasma are presented. The X-ray phase analysis revealed the presence of two crystalline modifications of titanium dioxide. They are annotated and rutile, and this fact is confirmed by the result of the transmission electron microscopy. The possibility of controlling phase composition by changing the main parameters of experiments such as oxygen concentration and supplied energy is shown. It was established that the particles obtained by the plasma dynamic synthesis method have a defect structure, which substantially led to a decrease in the band gap. This makes the resulting product promising for further research on photocatalytic properties. Thank you for your attention. If you have any questions, I'll try to answer to them.